Okay, we're going to talk about scatter plots today. And this is a statistic topic that we usually have not covered in the past. And it lets us do some cool things with your graphing calculator. So I think you're going to like it. So first of all, what is a scatter plot? A scatter plot is basically a way to graph some different data that you collect. So maybe a scientist or a statistician is collecting some information and they want to graph it. So for this particular graph, which we'll look at more on the next slide, you have all these dots, and the x-axis is labeled years since 2000, and the y-axis is labeled student enrollment. So what does each xy actually represent here? Well, the number of years, the number of students that year, well, kind of. This dot is the number of students that year. Maybe. Let's look what else we have here. The years since 2000. Well, the years since 2000 is what the X is representing. And now that we think about it, the number of students that year is what the Y is representing. So is it the number of years for each student enrollment? No. How about this one? A pairing of the year with the student enrollment of that data. So what could you make about this data? If you're going to make a statement, what could you say? You might see that this line is kind of trending up, like it might be increasing here. You could say that student enrollment is increasing in the years since 2000, or some statement such as that. So that would be looking at the trend, which is kind of what we're going to be doing today. We're going to use some models to approximate data sets and make predictions, and we're going to talk about this line and how good of a fit this approximation line can be. So we're going to decide if a line is linear or not. A graph is linear, okay? So all these dots look kind of like a line to me, but in this particular data set, these points, if I draw a straight line, every single dot will touch them. And in this one, that's not quite true. There's no way to draw a single line that would touch all of them. So we call this approximately linear. And usually when we collect data, you're usually looking at things that are approximately linear because it's kind of hard for something to be so perfect this way. So we use this approximately linear model a lot with statistics, and it really does a decent job of getting it done. So how do you know what type of relationship you have? Well, there's this word called correlation. And correlation is the general type of relation that two variables will have. So there are three ways that this could look. We call this a positive correlation because as X increases, Y increases. This is called a negative correlation because as X increases, Y decreases. And this actually kind of has no correlation at all. It's kind of random. It does very much align with slope. This looks like a positive slope line. This looks like a negative slope line, even though it's only approximately linear. It's not exactly linear. That's kind of the mindset we have when we're dealing with correlation. So what do you think about this correlation? Is it positive, negative, or no correlation? Well, if I was going to draw a line through here, it would be kind of a downhill slope, so we call that a negative correlation. If I was to draw a line through this point, I really wouldn't even know where to draw the line. Because of that, we would say that there's really no correlation here. Okay, now what do you do with that idea of correlation? Well, if the data is positively correlated, you might think that there's some sort of relationship here, right? So we're looking, and as the tree gets taller, someone has a tree and it's getting taller, and then they also have a salary. And it seems to be that as this tree gets taller, this person is making more money. So does that mean that as the trees get, is that causing me to make more money, the tree getting taller? No, we know that is ridiculous. We also know that because she's making more money, that is not making the tree get higher. This data is related positively, but this is a really big thing. Correlation doesn't tell us that one thing causes another. It just tells us that it's an uphill trend when you go up together. It says it does not cause effect relationship. Probably some of you have heard the saying, correlation does not imply causation. One does not cause the other, but simply there is a trend when you look at the two graphed together, but they definitely are not causing that. So you cannot assume anything based on the data. You can make some predictions potentially, but you can't assume that you know background information. So what type of correlation is this? Well, it looks like it's kind of a positive correlation, right? So let's see what we can say that's true about this graph. We have years since 2000 and student enrollment again. Each year, the number of students increases at a constant rate. If it's a constant rate, that means it has a slope, and it means that it is a linear function, straight linear. Does that look like it's happening from this year to this year? Did it go up at a constant rate? No, this is not it. Is the school's enrollment generally increasing? Well, yeah, it seems that way. So I feel good about this. Is the enrollment increase only because time went on? Is the reason the enrollment is increasing is because there's been more time? No, that would be a causation that you cannot assume. So the only thing you can say here is that they generally increase together. Okay, so trend lines. This is where it gets kind of fun. So there's no line here, but we can kind of picture a line. And the line definitely would not touch all the points. But we can make what we call a trend line by drawing a line where we think would be best and then finding the equation of that line. So that's what we're going to do. We're going to draw or sketch a line in here. And if I was going to draw a line or sketch one in here, I might go right about there. Feels like it's a pretty good estimate. Choose 2 points that actually end up falling on that line. So this one looks straight like it felt right there. And maybe this one. Let's pick these two guys. We will then just make the slope and write the equation of this line. So what do we think this point is here? It looks like it's maybe 5. This is 1,500. So maybe 5, 1,400. This point looks like it's 10. Maybe, looks like it's almost right in the middle here, but maybe a little bit more than the middle. Let's say 1,800. So we can find the slope. The slope would be the rate of change, which is y2 minus y1 over x2 minus x1. So that will be 400 over 5, which is 80. So the rate of change would be 80, or 80 students per year. So you can do one of two things. This suggests using point slope form, which is fine. That's y minus y1 is m, x minus x1. You pick whatever point you'd like, or you could do y equals mx plus b. That is up to you. If we do point slope form, let's pick the one with the 10 here. Y minus 1,800 equals m. We said that was 80, x minus 10. And you can leave it like that. Or you could pick your point, x and y, plug it into this equation. 1,800 is 80 times 10 plus b. Clean it up. 1,800 is 800 plus b, subtract 800, and b is 1,000. Then you can write the equation y equals 80x plus 1,000. So you could do point slope, or you could do y equals mx plus b to come up with an equation. Now, what can we do with that equation? Well, what we can do for that equation is we can make predictions. We can say, well, look, there's not a dot in here. I wonder what happened 4 years in 2004. So now what we can do is we can plug 4 into my equation and I can make an estimate. Okay, if you pick a point from your starting dot to your last dot, it would just fall right on this line, and that's called interpolation, coming up with an estimate between your data points. Now, this word extrapolation would be if I asked you what happened up here. What happened in 2020? That's not within my data set, but I could imagine that this line would continue on, and then I could come up with an estimate that way, and that is called extrapolation if it's outside the given points. So let's use the points here to find a trend line. Another practice, they gave me the 2 points. They drew a line. Their line looks like it's similar to mine, but their points were a little bit different. So let's use this one. Let's find the slope first. That'll be 1,900 minus 1162 over 11 minus 2. 1,900 minus 1162 is 738. over 9. Well, 738 divided by 9 gives me 82. So I got a little bit different slope here. And then we can use a point. Let's do mx plus b again so we can compare them a little bit better. If I pick 11, 1900, it'll be 1900 is 82 times 11 plus b. 82 times 11 is 902. Subtract 902, and you get b is 998. So the equation for this line would be y equals 82x plus 998, which is a little different than what I had before. When you find a trend line by hand, it happens that things can be a little different from one person to another. It's still a decent predictor. We can still interpolate between these 2 points and extrapolate on the outsides, but we might get slightly different answers, but they should seem reasonable. Statistics is not always extremely accurate. So let's talk about this equation of a line. They give us the trend line equation, and they want to know what would the earnings for sales be for $80. So if you have $80 in sales, what would the earnings actually be? Well, that was a point they didn't have. So what we can do is we can plug in 80 for x, and we can interpolate because it's in between the points. 0.3 times 80 is 24 plus 110. And we're interpolating that it would be $134 earnings. Well, if it's $0, that also does not show up here, right? We're counting by 40, so 0 would be here, but it's outside of my data set. This is technically extrapolation, and if you plug 0 into this equation, it's just the y-intercept, which would be $110. It's extrapolation. Now, 400 is way outside the data set. It's not even on my picture here. So when I plug this one, that is definitely going to be extrapolation. And it's 0.3 times 400 plus 110, which is $230. A decent estimate, but it's way outside my data set. What we want you to know is that it's less risky to interpolate. Since you have data in this area, if you're predicting within this area or close to it, it's less risky. You're probably going to have a decent estimate. It gets a little trickier when things are way outside. You're extrapolating far outside because other factors might come into play. So you need to be careful when extrapolating. Okay, here's another practice. Student enrollment year since 2000. This is the equation we came up with a minute ago. Use the equation to determine what the student enrollment was in 2003. Well, where would 2003 be? This is 2000. 1, 2, 3 would be right here, and it looks like they even gave me a green dot. What am I going to plug in my equation? It's 3 years after 2000, so that would be 82 times 3 plus 998. And the estimate of the students would be 1,244 students. We should label. Now, 2013 is just barely outside. This is technically extrapolation, but it's just barely outside the limit. So we're going to plug 13 in. It's a little riskier since it's outside of my data set. That's 2,064 students. It is important to know that just because interpolating happens inside and is less risky, and extrapolation is a little more risky, you're still going to make mistakes sometimes. Because like this point right here, that's pretty far off my line. What happened there? Well, something happened. But it doesn't, what if that was your data set? Maybe there was one right beside it. Maybe it was 2 years that it was down a little bit. But your estimate would be up here. That's okay. This is not perfect. It's just a tool to help us predict. Next, we're going to talk about the cool stuff. Okay, so the trend line we found by hand, and that's great. There's this idea called linear regression. It's also called a least squares line or a line of best fit. It is a trend line, but it is not a trend line the way we just eyeball sketched it through. Linear regression actually has a scientific method for finding it, In fact, whenever I was in college, they had us find it by hand, and it is really, really, really hard to do. We had to take all the differences of all these dots, and you had to find the distance and square it, and you had to place the line so that was in the right spot, and it was tough. But good news for us is our calculators can do this for you. There's also some regression calculators, I think, that maybe you can find online if you don't have a graphing calculator. If you have a Casio, feel free to make a YouTube search and look it up. If you have to borrow a calculator from me, if it shows up on an assessment, you're welcome to do so. So here's what we're going to do. And there's a lot of buttons to push here. First thing we're going to do is we're going to get our calculators out, and I'm going to write these down so that I'll be able to see them in a minute. We're going to plot these points in our calculator. So we're going to plot little dots on our calculator. Okay, so each pair represents an excellent basketball player's height, okay, and the points per game. So the height and the points per game. And they said it's going to be a linear regression model. Basically, I'm going to guess the taller you are, the more points you have, but let's see what happens here. Okay, so let me get my calculator out. I don't know how to escape through here. Okay. Okay, the first thing we're going to do is we're going to go to second. Everyone needs to hit second and then stat plot. First thing we're going to do is get ready to graph. You don't have to do this every time. See how it says plots off? We're going to hit 1 and then turn the plots on. And that way we're going to allow our graph to graph little dots for us. The next thing we're going to do is something you'll never have to do again. And that will be second 0, which is catalog. And we're going to scroll down until we get to a command that says diagnostic on. We're going to turn our diagnostic tool on our calculator. It defaults to off for some reason. And this is going to give us a little bit of information that will help us tell us if our line is any good or not. So then just hit enter and it will say done. Okay, so now that we're ready to graph, here's what we do. We're going to hit the button stat. This makes sense because we're talking about statistics. We will hit 1 for edit. So this basically looks like a table. I'm getting ready. I had some points in mine already. Oops. Okay, so we're going to treat this as our X column and this is our Y column. So we're going to enter the data in. So we'll hit 65, enter, and we'll hop on down. 68, enter. 73, enter. 77, enter. And 78, enter. Then hit the right arrow over, type in the Y values, 20. Okay, so we got these points in. So let's look at them, right? So if you hit graph, you'll look and you should be disappointed. Why? Because you see nothing. Don't forget what we talked about. We have to adjust our window. This goes from -10 to 10. So we're going to hit window. And actually, there's a shortcut you can do. You can hit zoom. And if you go down here to zoom stat, number 9, it probably will change the window for me to make sure all my dots are in there. So if you hit zoom 9, it will take you to show your pictures. Now, if you want to know how they did zoom it, if you hit window here, you can see they started their X at 63 and went to 79 and Y men to that. Okay, I kind of like it better when I start at 0. I'm going to start at 0 and 0 and see what happens. See how I look about that. Okay, so all my dots are over here. You might like that better. Again, you might like just to have it all zoomed in, but I like to know where my y-intercept is. So that's up to you. Let's look at it this way for now, but be careful. I don't want you to think that this would be the y-intercept. So let's find what the equation of the line would be. So let's go to stat. Now you're going to go over to calculate. And we are going to select linear regression, number 4 here, and it says AX plus B. You'll hit enter all the way down, and then it gives me some information. And this is the equation of my linear regression line. So my equation is going to be y equals we'll say 703 x minus 22.99. So if I want to graph it, clear this out, and I typed 0.703x minus 22.99, and I hit graph, you can see that this line can estimate those points. That's the line of best fit. If I change my window so that I can have the 0, 0, on here, you can tell better that that y-intercept would be in the negative range. That might help you understand your graph a little bit better, okay? But that's fine if you don't. The zoom stat is just fine. So we have that equation, 0.703x minus 22.99. Now, what do you think of that line? You think it's very good? It doesn't hit any of the points. Well, it's not our best line that we've ever seen. No, it's a positive slope, and this is where we're going to talk about next. How good is my line? Well, how can you tell if your line's any good? I don't think I answered a question here. Predict the average score of a basketball player who is 70 inches tall. So let's predict 70 because I didn't do that. I have my equation. I'm going to plug in 70 for x, 0.703 times 70 minus 22.99. You also could look at your table if you want. 0.703 times 70 minus 22.99. Looks like he's going to score 26.2 points. And I don't think 0.2 points makes sense, so we're going to go with 26 points. Okay, so we said we didn't like our line very much, and that's what's going to talk about next. There's this thing called a correlation coefficient, and the value is called R. So on my calculator when I was there, do you remember what the R said? My R said, stat, calculate, 4. My R here said 0.86. So what the 0.86 tells me is it kind of tells me my line's not so perfect. If my line was perfect and positive, it would have a correlation coefficient of 1. The closer it is to 0 is not very good. Usually the 0.99, the 0.9s are what you're looking for. Anything below a 0.9 is not very good in my opinion. So we're like moderately positive, which is what happened here. If there was negative slope, it would have a negative in front. But the closer to 1 it is, the better the slope line is, the better the predictor it is. So the correlation coefficient tells us how good our line was, and ours was just okay. So let's try one more example here. This time we have 0 through 8. So I'm going to go ahead in my calculator again. And I'm going to go to stat, edit. If you want to delete your thing, you go up to L1, hit clear, and then enter, and type in your values, 0 through 8. Or you could have just wrote right over them, and I might do that on this side. You can just write right over them. My second points were, what do we have here? 1,000, 1120, 1,000, 1162 was next, 1240, 1,400, 1,520, 1,580, and 1,680. Okay, so let's look at our graph this time. Oh, I messed something up. Was there no 0? 1,000, 1120, 1162, 1240, 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 5, 6, 7, 8. little booger. 0, so I'll delete this one. 0, 1, 2, 3, 5, 6, 7, 8. If your numbers don't line up, you will have a mistake. Like you have to have everything lined up. Okay, so let's hit graph. And there was that line from last time. I don't need it. Y equals, let's clear that out. Hit graph and, oh no, the dots aren't there. So you go to zoom, you go to stat, which is 9, and there's my dots. Okay, go to the window to see what's happening. I should be able to see the y-intercept if it's there, and they're really up high for the y values. So let's find the line. Hit stat, calculate. Linear regression is number 4. Enter all the way down, and there it is. 79.6x plus 1006.85. Let's see what we have here. Let's type that in. Y equals 79.6x plus 1006.85. Oops. Let's hit graph and see what you think. Oh, this line is much better. Don't you think this line is much better? So let's go look at the R value on this one again. Stat, calculate, linear regression. What was the R value here? Yeah, 0.99. This is a pretty good line. And you can tell by looking at the graph that is a pretty good line. This one's a little bit off, but everything else is pretty darn close to touching it. So that is a better positive correlated line with a higher R value. Okay, this is the review of everything we talked about in case you want to fix up your notes a little bit. And that's it for today.